Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, subarray distinct elements sum of squares 2. The problem is very interesting and is actually harder than usual hard problem of Leetcode. The submissions says it's all. So as always, we'll start from scratch. We'll try to dissect the problem step by step and arrive at an optimal solution. So with that, let's get started. The problem states that you are given a zero-indexed integer array nums. The distinct count of a subarray of nums is defined as the number of distinct values in that subarray. You have to return the sum of squares of distinct counts of all the subarray of nums. And since the answer can be large, you have to return it modulus 10 to the power 9 plus 7. So let's take an example. Let's say this is a given array nums 1, 2, 1. We have to take all its subarray and find out the number of distinct element in each of these subarrays. Whatever the count we will get, we have to do the squares of each of them and sum them and return that as a result. So there are 6 possible subarrays of this subarray. First subarray contains this one, second subarray contains only 2, third subarray contains only 3, right? Fourth subarray contains 1 and 2, fifth 2 and 1, and finally sixth one 1, 2 and 1. Now this one contains one distinct number, this one contains one distinct number, again one distinct number, this contains two distinct number, this also contains two distinct values, and finally this also contains two distinct number 1 and 2. We have to return the sum of squares of these values. So 1 square plus 1 square plus 1 square plus 2 square plus 2 square plus 2 square. The value will come out to be 15, and hence 15 is the result. So hope the problem statement is clear. Now how to solve this? Let's start with the brute force first. So what will be the brute force solution of this problem? The brute force will be very easy. You can just simulate whatever you have been given in the problem. You can simply take all possible subarrays, find out the number of distinct element in each of these subarray, square them, and return the sum as a result. So in this particular array, let's say you will start with each of the subarrays. So you will say, okay, this is my first subarray. I will consider all the subarrays that are starting from this particular L. So I will try out all possible R. So this is my first R. Basically my first subarray is this. I will figure out the number of distinct element. Number of distinct element is just 1, so I will just do 1 square plus. Now this is my second subarray, L2R. Number of distinct element in this subarray is 2, so I will just do 2 square. Then third subarray, 3 square, and so on and so forth. So I will try out every possible subarray that is starting from this particular L, and then I will try out every possible subarray that is starting from this L, right? So this is first subarray, second, third, fourth, and so on and so forth. So in the very same fashion, I will try out all the subarrays and finally return this result, this sum as the result. So what is the overall time complexity? What we are doing, we are iterating over all the subarrays. So in total there can be n square subarrays, right? Now for each of these subarray, what we need to do, we need to figure out the number of distinct element. So if you do it naively, it will take order n time to figure out the number of distinct element in a subarray. But because of this logic, like we are starting from this particular L, right? And then we are figuring out, and then we are traveling all R one by one. So when we are here, we can simply keep track of what we have already seen. So we can keep a hash map or an array, whatever you like. You can simply say, okay, I have already seen 5, right? Now next time when you go to some element, you will simply see what you have seen. If you have already seen that element, you will not increment your counter, otherwise you will increment your counter, right? So in that fashion, you don't need this extra n to figure out the number of distinct element in the subarray again. So overall time complexity is order n square, right? Now surely this will not pass because n is 10 to the power 5, so this solution will not work. We have to optimize this. Now optimizing this solution means that we need to get rid of one of these n, like, and where from these two n's are coming? These two n's are coming because we are iterating over all the subarrays, right? If we have to optimize it, we need to somehow try not to iterate over all possible subarrays. So we are trying out all L and R, right? So if we have to optimize, we need to figure out a way in which we will not iterate over all subarray and still get the number of distinct element of all the subarrays, right? Or the sum of distinct element of all the subarrays. So let's what are the choices we have? We have just two choices here. We can either fix L and we can say, okay, I will figure out some magic in which I will get the number of distinct element in this range, in this L2R, in this L2R, in this L2R, and so on and so forth. I will get the sum in all of these and in less than order n time. Now whatever sum I will get, I will keep it and then I will start my next L, and in the same fashion or with the same kind of magic, I will figure out what is the sum of distinct value or sum of squares of distinct value of all the subarrays starting at this particular n, again in less than order n time. So we can keep on doing this for all the L's. So in total we will be doing this n number of times, and each of these, as we mentioned, we have to do this in less than order n time. So this is one approach. Second approach could be just opposite. We can say, okay, I will fix R instead. So I will try all possible L's, right? So if this is R, I will try this L. How many, what is the count of, what is the sum of count of distinct number in all the subarrays that is ending at this particular index? Similarly, sum of count of distinct elements ending at this particular index. So this subarray and this subarray. Similarly, the ending at here. So this subarray, and this subarray, right? So these are the two approaches that you have if you have to optimize this. No other choices, right? So let's look at how this will look in action. So we have still the same array and we are trying out the second approach. Basically, we are trying to fix R, and for this R, I'm trying to find out what is the sum for all the L's for this particular R, right? So initially our R is at 0, right? So it means I want the sum of all the subarrays that are ending at this particular index. So for simplicity, the original problem asks us to find the sum of squares, but for now let's just stick with finding out the sum only. We'll look at how to find sum of squares. How they are different, we'll look at that afterwards, but for now we just want to find out the sum of distinct values, sum of count of distinct numbers in each of the subarrays ending at a particular R. So initially R is 0, so basically this is our subarray. We need to find out the number of distinct element in this subarray. There is just one subarray, so number of distinct element here is 1, right? Similarly, if R is this, so we have now two subarray, one this one and second this one. Notice we are only considering the subarray ending at R, so only two subarrays. So for this subarray, what is the count of distinct element? 2, 5 and 6. For this subarray, count of distinct element is 1, right? In the same fashion, for this R, this is the state. The count of distinct element in this subarray would be 3, distinct element in this subarray would be 2, and number of distinct element in this subarray would be 1, and so on and so forth. Now let's look at this value. Basically, when R is this, right, this particular state. So in this case, in all of these, what you can see, the count is simply 1 2 x. So 1 2 1 2 3 1 2 3 4 1 2 3 4 5, but This doesn't have this. And why? Because this is the first time we have a repeating element, right? Now what happens with the repeating element? Let's figure out the number of distinct element in this subarray. How many distinct element are there? 1, 2, 3, 4 and 5. 8 is not, 8 is repeating, so 5 distinct element. Similarly, count of distinct element in this subarray would be 4. Similarly, here it would be 3, and here also it would be 3, here it would be 2, and then 1, right? Now notice what's happening. From this to this, what was changed? We just added one new element, right? And what this denotes? This denotes the number of subarrays, or the number of distinct element ending at 5. So if we add a completely different element, the count will simply increase by 1. So this one will now become 2, and a new one will be added. In other words, whenever we are adding any element, let's see this, it will be much easier to see. Whenever we are adding an element, we want to find out the number of distinct element ending at this particular index, right? But we already have the number of distinct element ending at just the previous index. So we already have the count of distinct element for this one, for this one, and for this one. In all of these, I just need to append one more number and see what is the count now. So if I am appending a completely new number, in this case 9, then we are sure that everywhere the count will be increased by 1. So this 3 will become 4. It means the number of distinct element that starts at 5, that for the subarray that starts at 5 would be 4. Number of distinct element that of the subarray that starts at 6 would be 3, and so on and so forth. So if the number is distinct, the value will simply increase for everything by 1, and there will be one more 1 added. So if previously the count of, or the sum of count of distinct element ending at a particular R is 3 plus 2 plus 1 6, here it would simply be everything added by 1 and then one more 1 appended, right? So whatever the sum here would be would finally be the number of distinct count of distinct element, sum of count of distinct element for all the subarray ending here, right? This is the pattern that is continuing if we are adding a distinct element. But as soon as we are adding an element which is actually equal to something which we have already encountered before, this theory doesn't apply, because notice what we had the number of distinct element in this particular range. Now we are saying that I have added one more element which is actually equal to one of these elements, so the count will not change, right? This subarray already have all the numbers, or all the distinct numbers that we have seen so far, and if we are adding one more number which is actually equal to one of these, the count will not change. So this 5 would remain 5, right? Now what about this 6? In other words, what about the subarray that is starting here? Now the same thing, right? If 8 is already occurring here, the count will not change. In this case 8 was already there, so the count will not change. In the same fashion, for the next subarray as well, for this subarray as well, if 8 is already there, count will not change. So 3 remains 3, right? Now as soon as you crosses the last 8, it means all of the subarrays now will not contain 8 anymore. So for all of these subarrays, in other words, for the subarray 9, 7, 8, for subarray 7 and 8, and for subarray just 8, for all of these subarrays you will be having one extra distinct element. So this 2 will not remain 2, instead it will become 3. Similarly, this 1 will not remain 1, it will become 2. And similarly, there was a 0, let's say, afterwards, so this 0 will not remain 0, it will become 1, right? Again, just to reiterate, what happens is whatever is the last occurrence of 8, after that everything will be incremented by 1, right? So that's what is happening. Now, can we generalize this? Answer is yes. So we can actually generalize this, and you can see further as well. If we have added a 6, as soon as we crosses the last 6 or this particular index, everything else, for everything else, this 6 is a new distinct element. So for everything else in this range, we are adding 1. For everything before this, they remain as it is, right? So hope this observation makes sense. This is a very generic observation. You like, this is actually the piece where in which you will be finding out the number of distinct elements in a range. So this is a standard technique for that. Basically, just look at the last index which contains the same element, because after that only this index will be considered a different element. Before that, this index already exists, kind of, right? So what is our approach now? Remember what we need to find out? We need to just find out the count of distinct element for all the subarrays ending at a particular r, right? So that's what we need to find out. And for the first subarray it is easy. We know the answer would always be 1. For the second subarray, what we will do, we will simply see what is the total or what is the number we are adding, and where this number exists in the already existing array that we have taken care of. So we have already taken care of 5. Does 6 occur in this array? The answer is no. So we have to add 1 to everything else. So we simply added 1 here, and there was 0 afterwards, so we simply added 1 to both of them. Similarly, 8. Does 8 occur anywhere before? No. So we simply added 1 to everything until the current index. So there was 0 here, so this will now become 1, right? In the same fashion we will continue. So this is our overall trick. So let's just look at it one final time. Let's say this is the array. What is our algorithm? Algorithm is simple. We will simply figure out what is the count of number of distinct element ending at a particular r, and for that what we have said is we'll simply see where does this 5 exist in the previous array. So does 5 exist in the previous array? Answer is no. So simply add 1 to everything until 5, right? So simply add 1 to this particular piece. So we just simply add 1. Now just take the sum across all of them. This will be coming as 1. So this means the total sum of distinct element across all the subarrays ending at this particular r is 1. So we'll simply add 1 to our result, right? Now what happens is we moved our r. So we need to find out the number of subarrays, count of distinct element of all the subarrays ending at this particular r. So again, does 6 occurs anywhere before? Answer is no. 6 occurs just before this. So we have to increment 1 to everything here, because for everything here 6 is actually a new element. So we will simply increment 1 here and simply add 1 here. So the sum now is 3. It means the sum of distinct element across all the subarrays is now 3. So we'll simply add 3 here, right? So this one was all the subarray ending at 5. This 3 is the sum of distinct element of all the subarray ending at 6 or index 1. Now in the same fashion you will do the next one as well. Basically for this particular r, you will again say 8 doesn't come before, so you have to increment 1 to all of these, right? So simply increment 1 to all of this. It will become 3, it will become 2, and it will become 1. Now for actually finding out whether an element exists or not, you can use something like last seen array. So if for example, if r is this, you need to actually figure out where does 8 comes. So for if you have already keep on maintaining where you have seen a particular element, you can simply look up it here and say where does R occur. So for simplicity, you can fill everything with -1. Basically, the element doesn't occur anywhere till now, and whenever you see an element, you will simply make the change. So for whenever you have seen 5 or you have taken care of 5, you simply say I have seen 5 last at index 0. Similarly for 6, I have seen 6 last at index 1. For 8, I have seen 8 last at index 2, 9 index 3, 7 index 4. Now whenever you reach this particular index, you can simply look up this array, look up 8 in this array. You know where this element last occurred. So this is occurred at index 2. So you can simply say I will add 1 everything after index 2 until the current index. So I will just add 1 to this particular range, and similarly I will figure out the sum, right? So hope this entire algorithm makes sense. How the pseudocode will look like. Pseudocode would simply be this. As mentioned, we will have two arrays, last sin and frequency. So for each element, we'll try to figure out what is the count of distinct numbers sum for all the subarrays ending at a particular index I, right? So this is our R. Now as mentioned, we have to add 1 to everything after the last index or the last occurrence of that element. So we'll simply add everything from st to ed. Now once we have added everything from st to ed, we'll simply sum the frequency array. So this is simply adding 1 from this from st to ed index, and then we will simply do the sum of frequency array and add it to our result. Now this final result will contain the total sum of distinct element across all the subarrays, right? But we don't need to find out this, we have to actually find out the sum of squares. So we'll come to that. But what is the time complexity of this entire solution? See what we are doing. We are iterating over all the indexes, and after that we are actually adding 1 to a particular range, and then we are actually summing up a particular range from 0 to n. So if you do it naively, this is order n operation, right? You may have to add 1 to all the indexes, and this is also order n operation because the size of the frequency array is n. But because this is range update and range query, you can actually use range data structures like segment tree. So you can simply use range query data structures, and this can be done in log n time, addition of 1 in a particular range, and this also can be done in log n time. So we already have a series on segment tree where I have discussed segment tree from scratch. If you don't know about segment tree, you can watch that. I will link that somewhere in the description down below or in the top right section. We haven't discussed the range updates, which will be required here, but we will be covering that very soon, so stay tuned. I will be giving you a brief overview of how range updates will work, but the overall complexity now is order n log n, which is sufficient to pass the given constraint of the problem, right? So notice this is just finding out the sum, not the sum of squares, right? So let's first look at the range update. So if you are already aware of range updates, just skip to the next section. The timestamps are there in the description down below. So this is how a usual segment tree looks like. We have the array elements in the leaf, right? And for each of the non-leaf node, we store some property of all its children. So this says that here we are storing sum. So this says that in 0 to 1 the sum is 3. Similarly, it says that from 2 to 3 the sum is 7, and similarly it says that from 0 to 3 the sum is 10. You can actually do the sum. 2 plus 1 plus 3 plus 4 is just 10, right? So this is how segment tree looks like, right? Now let's say you have to add 1 in the range 0 to 3. That's what range sum means, right? So if you do it naively, like you are adding 1 to everything between 0 to 3 in segment tree, what you have to do, you will just go to index 0 and add 1. this will take log n time. Similarly, then you will go to index 1, add 1 log n time, go to index 3, index 2, add 1 log n time, and index 4, add 1 log n time. So in total you will take n log n time just to make a particular update, which is very slow. This is actually slower than the brute force solution, in which you will take just order n time to update any particular range L to R. So what range updates does is, it basically not propagate the change all the way down to the leaf. Instead, it will only keep the change to itself. So we know that we have to update everything below to +1, right? So we have to do +1 here, +1 here, +1 here, and +1 here, right? Instead of actually doing these values change, I will simply say I actually need to add +1 to all the leaf node beneath me. That's it. As soon as you do this, everything now change. You are not updating n log n nodes. Instead, you are just updating log n nodes, because any range, you know that any range can be divided into log n number of ranges. So any range, if you are given to update any range L to R, you can actually divide this L to R into log n number of ranges, and each of these each of these ranges, you will simply say I need to add 1 to all my children. So immediately your complexity now becomes log n for a particular range update. Now how this would help? Notice that you still need a sum of all the element, but if you just keep 1 here, the sum of element is still 17, but actual sum is changed. This will now become 3, this will become 2, this will become 4, and this will become 5. So the actual sum here would be 21. But because you actually haven't propagated the updates to the leaf yet, the sum hasn't changed. So for that, what you will do, you will actually give a hallucination that you have actually updated, and you actually propagate the updated value upwards. So instead of saying that the sum of below thing is 10, you know that you have to actually add 1 to all its children, and you already know that there are 4 leaf nodes beneath me. How? 3 minus 0 plus 1. So you will simply propagate 14 here instead of propagating 10, and once you propagate 14 plus 1, 21, and this sum will become 21, right? So that's the overall picture of how range update actually does update a particular range in log n time. Now think about this. If you what we were doing, we were actually giving a hallucination of okay, I need to update everything or add everything to +1 in this particular range 0 to 3, but I haven't added it, and instead propagated the final sum, which would have been the result. So how we are able to calculate the final sum? Because we already know the number of children here, so I can simply do plus number of children, and that will be my final sum, right? But when you do sum of squares, this is no longer true. So let's say you again have to update this 0, 3, right? You have to update you have to add +1 to everything here, right? So this 2 will become 3, this 1 will become 2, this 2 will become 3, and this 3 will become 4. So this 9 will become 16, this will become 9, this will become 4, and this will become 9. So at this stage, can you propagate the final value without actually updating everything here? So with just 18 with you, can you give the final result of 3 square plus 2 square plus 3 square plus 4 square here? If you are able to give this, then you can apply lazy propagation. Otherwise, lazy propagation will not work. You have to actually go and update everything. And if you are going and updating everything, it will be no better than order n log n, which is something we can't afford. We just have the buffer for log n time, right, with us. So that's where you have to think of a particular trick. So what we are doing, this value is a square plus, let's say this is a, this is b, this is c, and this is d. So this value is a square plus b square plus c square plus d square. What you want? A plus 1 square plus b plus 1 square plus c plus 1 square plus d plus 1 square. So how will you compute that value directly from this a square plus b square plus c square plus d square? So for that, let's just try to look this up. Instead of 4 terms, let's say we have just 3 terms here, a square plus b square plus c square. And what we want to compute the value of a plus 1 whole square plus b plus 1 whole square plus c plus 1 whole square. So if you just expand this value, this will come as a square plus 2a plus 1, b square plus 2b plus 1, c square plus 2c plus 1. And if you rearrange the terms and just take whatever square terms are there in a single bracket, and then the 2a, 2b and 2c terms in a single place, and then the actual value or the actual constant term in a single place. Now see, you already know the value of this, right? You have this stored here in the current node. So this you already know the value. This is constant. You can actually figure out this. What will the value here? This will simply be the number of children, right? So number of terms, which is equal to number of children. This you already know. This the value of this would be r minus l plus 1, right? Now what's left? This is left. So what you want? You want the value of a plus b plus c, or in other words, you want the sum as well. So instead of just maintaining the squares, we'll maintain two things in our segment tree. We'll also maintain the sum here. So instead of just maintaining 4, 9 and everything, we'll also maintain the sum here. In other words, this is how the segment tree would look like. This will now become, let's just get rid of this ABCD. So this will now become 5, 3, because 2 plus 1 is the sum. 13, 5, 3 plus 2 is the sum. Similarly 18, let's just get rid of this, 18, 8, 3 plus 5, and so on and so forth. Now whenever you are saying that add 1 to everything below me and I need the final result, what you can simply do, you can simply say 18 plus 2 into 8 plus r minus l plus 1 or plus 4, and that will be your result, right? So you can actually provide the actual value after maintaining two things, the sum of squares and the actual sum. So that's the only thing that will change to convert this solution to give us the sum of square, actual sum of distinct numbers to the sum of squares of distinct numbers, right? So if you have watched till this point, I would highly encourage you to pause and try to code this entire thing by yourself and get it submitted as well. If you don't know about segment tree at all, you can refer to segment tree videos. And for now, I would encourage you to not worry about segment tree. I have a class of segment tree implemented, which has two methods, which has just one method useful, add 1. Basically it will add 1 to everything between x and y, and you can query this square value of 0 to get the final sum. So you can simply utilize the segment tree as it is. You can copy paste and just try to code the rest of the logic by yourself. So hope you have at least tried it once. So let's now look at the code finally. The code is exactly what we have discussed. This is the last position or the last scene array. We have a segment tree. We find out the st and ad, basically where we need to add 1, which range we need to add 1. So we just simply call add1 function and just do addition in this range. After that, as mentioned, this tree dot square 0 will contain the final sum or the sum of squares of the frequency array, right? We'll simply add it to our result and also update the last scene array. Let's look at the segment tree code as well. As discussed, this lazy will say what this lazy is basically this value which we are saying that we will propagate afterwards if required, right? And along with this, if you remember, we are maintaining two things, sum of squares and the actual sum. So we have two things, sum of squares, actual sum and sum of squares. So what we are doing in add one, we simply update the lazy. This is like the usual segment tree process, and we just see if current range is completely within this x comma y. If it is, I will simply update the current position and see we are not going downwards. We are simply saying that lazy is 1 and returning this update lazy thing. We'll look at this update lazy, but this is what we are doing. We are not propagating this 1 downwards. Instead, we just stored 1 here and say I will update later, right? And we'll provide hallucination to the next things. So after this entire thing is done, we have to update these values just like usual updates in the segment trees. Now update lazy is basically saying I need the final value of this node without this to be done thing. So this I will make it 0, and if it is 0, what is the value here? That's what we need. So that's what update lazy is doing. So basically if you want the actual value, you actually push one below, because you are not updating the below nodes in the current iteration. You just simply push whatever is the change below, and for this you will find out the actual value. And what is the actual value? As discussed, it will be sum of squares plus 2 into the sum plus the actual number of nodes, or number of nodes in the leaf array. So so this is just for if we are doing plus 1, right? But it may happen that you have accumulated some of the pluses here, so this 1 may be x as well. So what will be the final result? Basically it will simply be multiplied by x square here, and this will be multiplied by x here, right? So that's what we have done. The new sum would simply be lazy I into gap. Gap is the number of elements, right? The final sum of squares would be sum of squares already, which is this piece, plus the value x, right, plus the sum, multiplied by sum and multiplied by 2, and finally x square multiplied by number of elements. So we simply update this sum and square, which will update this number actually, and we actually propagated 1 downwards, so that if we need, we can compute the actual values of these nodes with this lazy array. So hope the entire solution makes sense. If you have any doubts in any of the piece, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.